Here now we'll start off the colligative properties, talking about four different types of calculations. And so the first one is Raoult's law. And what it's a simple relationship that the pressure of a solution is equal to the mole fraction times the starting pressure of the solvent. And the key thing here is they're all in the same perspective. So the solution's vapor pressure is coming from this solvent. So P of A is equal to mole fraction A times P A naught. All right. So the biggest problem people make is they use this wrong mole fraction here, is that we need it in the um, with respect to the solvent here. We're most used to molarity where we're looking at the solute, and here we're looking at the solvent. And so the in order to do this, then we get this trend where the pressure goes to zero when the mole fraction goes to zero. And when the mole fraction is one, we get the vapor pressure of the pure component. So that gives us a nice linear trend. So when we're in between here, we can get that correlation. All right. And so just to talk about how's this working, is that just when we have more and more stuff in here, it's blocking the ability of the surface ones to be the solvent. So the solute occupies more and more space here, and that shifts the equilibrium. So a little complicated, but the simple relationship, the common mistake, and the calculation should be straightforward. What this leads to then is the boiling point elevation then. And so um, the the change in the boiling point is equal to kbm. All right, and it's just a constant for the different solvents. They have different constants, and so that are given. Oh, I thought that was there. Sorry, and times the molality. And so what we get then is the change in boiling point. And what I like to do is to get that change and then use the expression boiling point elevation, freezing point depression. And so what happens is that this is going to look very similar for freezing point, but you're going to have the opposite shift. So mentally, what I do is I calculate what's the change in boiling or freezing, and then say, is it below or is it above the starting point for the solvent? All right. Moving on, looking at freezing, you'll see that again, delta TF is equal to KFM, same thing, but here this is what's flipped then to accommodate for that shift. And it's so hard to remember that, but just empirically, everybody can correlate boiling point elevation, freezing point depression. And what's nice is boiling point elevation is explained by Raoult's law. So if you add a solute, the vapor pressure goes down. So that means you have to heat it hotter in order to get to the same vapor pressure. So that's what leads to boiling point elevation. And freezing point depression then is the exact opposite. All right. So straightforward calculations in there, you would be given KF or KB most of the time in order to solve for it. There's the select problems where you're given the other variables, T, delta T, and M, and you're asked to solve for KF. Additionally, you have the harder problems, which you'll find on the example site, where you have to calculate the molality in situ. So just kind of adding two easy calculations together makes it medium or hard. So you'll need to be rock solid on it. The last one, which is very different, is osmotic pressure. And so here it relies on a semi-permeable membrane. And um, and so the relationship is the same as the ideal gas law. We have pressure is equal to nRT. All right. So if we rearrange this and we say PV equals nRT, that's ideal gas law. So often though, because we're working with the solution here, then it's more common to take N over V and convert that to molarity. So we get a different form, but hopefully you already know this then from the first semester, fall Gen Chem, and the gas constant is the same. So you can look then at some calculation in here that given the amount of grams of sodium chloride, then calculate the molarity. Once you get the um, the molarity, then use the gas constant and the temperature, and we can calculate osmotic pressure. So it should be a straightforward, simple problem. One thing that is common on these is the determine the molecular weight. I didn't put that on the simulation for it, but after you master all those, you should look at making sure you get that conceptually. But that's pretty much it for colligative properties.